everybody. Welcome to the second part of our unit on electric current, resistance, and Ohm's law. In this part, we're going to focus in on what exactly is current. So I'm going to begin with a question. You have two options from getting from point A to point B in the wilderness. You can take the short route, but it is through heavy undergrowth, making it really slow and hard going. Or you can take a longer route that is clear to most obstacles, allowing you to travel more quickly. This is the option that electrons in a circuit face. As we saw in the last section when looking at the battery, there was a short route from anode to cathode, but you had to go through that membrane, the semi-permeable membrane, making it really hard to get there. Or you could go out and around. Easier, but longer. The electrons invariably will choose route 2, which is known as the path of least resistance. Okay. For this to work, what do I need? I need my battery. So here we are with my battery. And I need to connect from the anode to the cathode. One wire will do it. Now the problem with this is, yes, this is a complete circuit, but as it's drawn, it is also a short circuit. If you do this with a battery and you're holding it all with your fingers, you will burn your fingers because that's going to get really, really, really hot. And the reason is because the resistance is very, very, very small. Okay, so let's modify our circuit to make it a little bit harder for those electrons to flow. And what I'm going to do is I'm going to add, let's say, a light bulb. Oh, I am not drawing my light bulb very well. I'm going to try again here. Here I go. Dr. Murphy, what are you doing? Well, if you actually get an old light bulb and you look at it, that's where the electrical connections are. So I'm actually wiring my light bulb properly, if you will. One connection is to the threaded portion on the side. The other connection is to the bottom. And there is a black ring, usually it's black, that separate the two pieces, which separate them electrically, and that's why that ring is there. Same thing if you look at if you can get inside and look at a light socket. Remember, don't stick your fingers in a light socket, but if you get in there and you look, you can see the two connections there as well. Okay, so I went through a light bulb, and now I have a connection that goes all the way around. My light bulb will turn on. Yay, look at it glow. And I have a complete circuit that is actually safe and not a short circuit. Remember, short circuits are the things that cause your house to burn down. We do not like them. I can also take, and this will probably erase more than I want. Oh, yep, it did. But if I do this, and it's an almost complete circuit, but there's this gap. This gap causes what is known as an open circuit. And now, since I have an open circuit, all my lovely light no longer is on because it's not connected anymore. That's what a switch does, is it breaks the complete circuit so that the electrons no longer have that path from one to the other. Okay, so complete circuit. So, you have birds sitting on a wire. Why can these birds sit safely on this wire like that? And the answer is because one part of the circuit's in this wire, another part of the circuit is in that wire, so to complete the circuit you have to span across both. They're not, they're just sitting on one. Therefore, they're not completing the circuit, therefore no electricity flows through them. Now you may be wondering, what's this third wire for? Well, remember when you plug something in, typically you have three prongs. You have a hot, a neutral, and then you have a ground. Same idea here. Third wire for that purpose. Well, related question. Why are electric lines roughly 1 meter apart? And it's really the same answer. I need to be able to get up here and work on this wire without having to worry about hitting this wire, because if the bird wings, when it flaps, hit both wires, or when the lineman is up there working on the lines, if he touches both wires, that completes the circuit, and that's not good for anybody or anything. So the lines are roughly 1 meter apart in order to provide space so that we can get up there and maintain these without having to worry about accidental electrocutions. Okay, but when I have a complete circuit, I am now providing a path for the electrons to flow from the anode to the cathode. So if I go back to my battery, here's my battery. I'm going to provide my electric circuit, and this time I'm just going to draw the light bulb as a squiggle. Okay. If you look at standard like AA or D cell battery, the end of the knob is the plus, the positive end. So that would be the cathode end, which makes the other end the anode. Okay. Now, what happens? The electrons flow out of the anode, around the circuit, and into the cathode. Okay, so it's the electrons that flow. And we can calculate the current. How many electrons, how many charges flow past in a given amount of time. Now you're looking at this and going, oh, really, Dr. Murphy? I for electric current. Well, you don't want E again. We've already had too many E's, too many energies and electric fields, too many E's. Remember, C is taken. C is invariably the speed of light. We're not going to use C here. So what I like to think happened was that physicists went looking through the alphabet until they found a letter that really hadn't been used yet, and they settled on I. And here it is. If you're an electrical engineer, they actually use J. No end of confusion there. Okay, so electric current is a measure of how much charge flows past a point in a given amount of time. This is completely analogous to current in a river. Current in a river is a measure of how much water flows past a given point in a certain amount of time. And the larger the current in the water, the faster the water is moving. Okay, so current is charge per time. Okay, well, we know what really happens. We have electrons that flow out and around from anode to cathode. But there's a little bit more history here. Because when they were first starting to learn about electric circuits and how things were working, what they did is they said, okay, we don't know what is really happening. So what we're going to say is it's positive charges that are flowing out and around, out of the positive end of the battery and into the negative end of the battery. And that is the convention for electric current direction. It's the direction of the flow of positive charges in a circuit. And you'll be like, oh, really? Here's the thing. It doesn't matter. There are two negatives, and as we all know, a negative times a negative is a positive. So what are the two negatives? Well, we're flipping the sign of the charge. Instead of positive flowings, we know it's now really the negatives that flow. And the other thing we're flipping is the direction. So we can envision this as positives flowing one way or negatives flowing the other. And as long as we're good about how we do it, we're going to be fine. It's not a problem. So you can think about positive charges flowing out of the positive end of the battery without any issues here, which is good for history. Now, I don't think I opened up my simulation, but that's okay. We'll get it open here. Okay, so this is the same simulation you use in the circuits lab. Click on intro. I'm just going to wire up a very basic single bulb circuit here. One light bulb, one battery, and two wires. You could technically do it with one wire if the wire could bend, but the wires in this simulation don't bend so well. So here we are with two. And notice they've properly modeled the electrons flowing out the negative end of the battery through the light bulb and then coming back into the positive end of the battery. The other thing that notice is that for every electron that enters the battery, one leaves. And the same thing for the light bulb. As an electron enters the light bulb, another one leaves. And the point here is the current isn't used up. The electrons don't just get to the light bulb and stop. They flow in and they flow out. The current is the same everywhere in this circuit. Okay. So in versus out. The number of electrons that flow into a circuit element equal the number of electrons that flow out of that circuit element, and current is not used up. Let's do an example here where we do a calculation of electric current. So we are told the current, 20 amps. And this is a time, but it's in minutes. So I'm going to convert that to 300 seconds. 5 minutes times 60 seconds per minute. So current equals charge divided by time, which means the charge is going to equal the current times the time. 20 amps times 300 seconds is 6,000 coulombs of charge that flow. Now, as an aside to this, as an additional question, I can now ask, well, how many electrons does that correspond to? And for that, I bring this formula back forward. My total charge is 6,000 coulombs. N is the number of electrons, and in this case, I'm going to multiply by 1.6 times 10 to the minus 19 coulombs per charge, or coulombs per electron, however you want to think about it. And that results in 3.75 times 10 to the 22nd charges that flow through this circuit in those 5 minutes. 20 amps is a very, very, very large current, which is why you need your window AC units. You have to be careful if you put multiple on the same circuit because you'll blow your electric circuit, flip the breaker, if you will. Also, sometimes they have to be wired not into a standard outlet, but into one that provides a larger voltage. This concludes this section. In the next section, we're going to be looking at Ohm's law.